Download this code from codegive.com, link in the description below. A deep dive into sending and receiving data size with sockets in C. Sockets are a fundamental building block for network programming in C. They allow processes to communicate with each other over a network. One of the crucial aspects of reliable communication is ensuring that the receiving end knows how much data to expect and receives that exact amount. This tutorial will cover best practices for sending and receiving the size of the data payload before the actual data, providing a robust and predictable way to handle socket communication. Why send the size of the data? Simply sending data through a socket without indicating its size can lead to several problems. Truncated data. The receiving end might read only a portion of the data if it doesn't know the total size. Buffer overflows. Reading more data than expected could lead to buffer overflows, causing crashes or security vulnerabilities. Incorrect interpretation. The receiver might misinterpret partial data as complete, leading to logical errors in the application. Blocking issues. Without knowing the size, REQV, calls might block indefinitely, waiting for more data that might never arrive. Sending the size as a separate initial communication makes data transfer more reliable, predictable, and manageable. Core concepts. 1. Socket creation. Creating a socket is the first step. This involves specifying the address family, example AF_INET for IPv4, socket type, example SOC_stream for TCP, and protocol, example IProto_TCP for TCP. 2. Binding. Servers bind their socket to a specific IP address and port to listen for incoming connections. 3. Listening. Servers then enter a listening state, waiting for client connections. 4. Connecting. Clients attempt to establish a connection to the server's IP address and port. 5. Sending data. Data is sent using the send, or sendle, functions. Crucially, we'll send the data size before sending the actual data. 6. Receiving data. Data is received using the REQV function. We'll first receive the size and then receive the specified number of bytes. 7. Error handling. Thorough error handling is critical in socket programming. Send and REQV can return errors, negative values, indicating connection issues or other problems. Errno provides more detailed information about the error. 8. Closing sockets. After communication is complete, sockets should be closed using close, or shutdown. Key functions. Socket, creates a socket. Bind, binds a socket to an address and port, server side. Listen, listens for incoming connections, server side. Connect, connects to a remote server, client side. Accept, accepts an incoming connection, server side. Send, sends data over a socket. REQV, receives data from a socket. Close, closes a socket, or shutdown, for more controlled closure. Tunnel, /entall, converts host byte order to network byte order and vice versa. This is essential when sending multi-byte data, like the size, between systems with different byte orderings, NDNS. Network byte order is big-endian. Tons, /entos, converts host short, 16-bit, byte order to network byte order and vice versa. Byte order, NDNS. Different computer architectures store multi-byte data, like integers, in different orders. The two main orders are big-endian *. The most significant byte is stored first, at the lowest memory address. Asterisk little endian asterisk the least significant byte is stored first. Network protocols use big endian, network byte order. If the sending and receiving machines have different endians, you must convert the data to network byte order before sending and convert back to host byte order after receiving. This is where HNL, ANTAL, HNs, and ANTOs come in. The general procedure. 1. Server setup asterisk. Asterisk create a socket. Asterisk bind the socket to an address and port. Asterisk listen for connections. Asterisk accept a connection from a client. Asterisk receive the size of the data, in network byte order. Asterisk convert the size to host byte order. Asterisk receive the data payload based on the received size. Asterisk process the received data. Asterisk close the sockets. 2. Client setup asterisk. Asterisk create a socket. Asterisk connect to the server. Asterisk determine the size of the data to be sent. Asterisk convert the size to network byte order. Asterisk send the size to the server. Asterisk send the actual data payload. Asterisk close the socket. Code example, server. Code example, client. Compilation asterisk. To compile the server. To compile the client. Running the example asterisk. 1. Run the server, /server. 2. In a separate terminal, run the client, /client. Explanation and improvements. Asterisk error handling asterisk the example includes basic error checking after each function call. In a real-world application, you'd want to handle errors more gracefully, example logging errors, retrying operations, sending error messages to the peer. Check the errno variable for more specific error information after send, and reqv. Asterisk sendle, function, important the send, function might not send all the data in one go. It can return the number of bytes actually sent, which might be less than the total amount you wanted to send. To ensure that all data is sent, you should use a sendle, function that repeatedly calls send, until all bytes have been sent. The following is an example of the sendle function. Use this within the client code, replacing send. This should be done when sending both the size, and the data. Asterisk reqval, similarly important the reqv function might not receive all the data in one call. It can return the number of bytes received, which might be less than the total amount you expected. Use a reqval, function that calls reqv, repeatedly until all bytes have been received. The server code includes an example of this using a loop and bytes _to _receive. Asterisk data types asterisk using uint32_t for the data size ensures that it's always an unsigned 32-bit integer, regardless of the architecture. Asterisk dynamic memory allocation asterisk the server allocates memory dynamically using malloc, to store the received data. This allows you to handle data of varying sizes. Remember to free the allocated memory after you're done with it to prevent memory leaks. Asterisk buffer overflow protection asterisk the server allocates data _size +1 bytes for the buffer and null terminates the data, preventing buffer overflows when processing the data as a C-style string. Asterisk non-blocking sockets asterisk for more advanced applications, you can use non-blocking sockets. This allows your program to perform other tasks while waiting for data to be sent or received. You can use fcntl to set the O_non-block flag on the socket. With non-blocking sockets, you'll need to use select or poll to monitor the socket for readability/writability. Example with sendle in the client asterisk. Important considerations asterisk. Asterisk security asterisk sockets are vulnerable to various security attacks, example buffer overflows, denial of service. Always validate data, use secure coding practices, and consider using encryption, example TLS/SSL, for sensitive data. Thread safety. If your server handles multiple connections concurrently, you'll need to use threads or other concurrency mechanisms to handle each connection in a separate thread/process. Ensure proper synchronization to avoid race conditions. Network latency. Network latency can affect performance. For high-performance applications, consider using techniques like asynchronous I/O, example ePOL or CTWU, to handle multiple sockets efficiently. Keep alive. Sockets can be kept alive by periodically sending data. This is crucial for detecting broken connections. Blocking versus non-blocking sockets. Select the appropriate socket mode, blocking or non-blocking, based on your application's requirements. Non-blocking sockets offer more flexibility but require more complex event handling. Shutdown. Using shutdown to close a socket allows you to specify whether you want to stop further sends, receives, or both. This gives you more control over the connection closure process. Protocol design. Consider designing a well-defined protocol for your application that specifies the format of messages, error handling, and other aspects of communication. This detailed tutorial provides a solid foundation for understanding how to send and receive data size information with sockets in C. By implementing these techniques and following the best practices, you can build robust and reliable network applications. Remember to always prioritize error handling, security, and proper memory management. Good luck.